Hello, Psych299 Statistics. This is Larry Hatcher. We're now up to Unit 4. This is Part 180, the Correlation Coefficient Introduction. I'm going to cover basic concepts in the Pearson correlation coefficient, show you how to interpret and make sense of scatter plots. This is all ultimately going to lead to a YouTube TED Talk video in which you'll look at an animated scatter plot, and that in turn will lead to a Canvas quiz in which you'll answer some questions about that video showing the animated scatter plot. Let's get started. I am on page 180-7. Obviously, this is not the first page in the module. The first 6 pages of this module in your Psych299 course pack, the blanks should be filled in, except there's a couple of questions at the end of the module that I left open in case we want to do some kind of a small group discussion exercise. But we can skip past that, and we will begin taking notes on page 180-7, the section that's headed Introduction to Correlation Coefficients. Now let's begin with definition. Correlation coefficient is a sample statistic or population parameter that indicates the degree of relationship between two variables. Now, before I go further, let me say this is one of the most important concepts in a statistics class. If you're a psych major, you're going to read a lot of textbooks, a lot of journal articles where they report Pearson correlation coefficients. So one of the basic skills as everybody comes out of stats class needs to be able to interpret and make sense of Pearson correlation coefficients. There are many different kinds of correlation coefficients. Spearman rank order correlation, point by serial correlation in psych. Most popular one is the Pearson correlation, symbol for which is lowercase r in italics, also called Pearson product moment correlation coefficient. With most of our stats, I begin by talking about under what circumstances is it appropriate to use this statistic. It's appropriate to use the Pearson correlation coefficient when you wish to investigate the relationship between two variables. Both of the variables are quantitative variables. They're assessed on either an interval scale or a ratio scale. Those are our two highest levels of measurement. Relationship between the two variables must be linear. It can't be nonlinear, curvilinear. A little later I'll show you some graphs that illustrate what I mean by linear versus nonlinear. There's some additional statistics we need to worry about. Things like homoscedasticity. A little bit later I'll define terms like homoscedasticity, and I'll show you some figures that illustrate what it looks like when you have it and what it looks like when you do not have it. Let's begin with fictitious research investigation that'll be the source of Pearson correlation coefficients that I talk about in this module. Health psychology example. I'm on page 180-8 right now. Health psychology example. Assume you wish to identify variables that are correlated with number of minutes of aerobic exercise per week. This will be the criterion variable in your study. This will be the outcome variable in your study. You need a predictor variable to predict values on this outcome variable. Possible predictor variable in this study might be the health motivation scale from our questionnaire on healthy eating, which appears in an appendix of the course pack. We've looked at the questionnaire in previous modules. In this case, we're going to focus on one of the scales that measures health motivation. Sample item on the health motivation scale. It's important to me to be healthy. Scores on the health motivation scale can range from 1 to 7. Higher values indicate greater motivation to stay healthy. So this is going to be the pair of variables that's going to be the focus of most of my examples in this module. We're going to look at the relationship between health motivation and minutes of weekly exercise. Is it true that health motivation is correlated with minutes of weekly exercise? Is it true that people that score higher on health motivation will actually engage in more minutes of weekly exercise? Score high on health motivation, that means it's important to you to stay healthy, or so you say. Minutes of weekly exercise is what it sounds like. How many minutes of aerobic exercise do you get in a typical week? This pair of variables would probably be appropriate to investigate with Pearson correlation. Both of them are quantitative variables. Health motivation is probably measured on an interval scale of measurement. It's measured with a multiple item summated rating scale, and we generally assume that variables measured with multiple item summated rating scales probably measured on an interval scale of measurement. Minutes of exercise is on a ratio scale. You have different values. The values represent number of minutes. There's equal intervals between consecutive values. There's a true 0 point. If somebody says, I exercised 0 minutes last week, that's a true 0 point. So, okay, on the surface at least, it looks like these would be appropriate variables to investigate with Pearson correlation. We come to the topic of scattergrams. I'm still on page 180-8. Toward the bottom, page 180-8. I'm going to spend a lot of time talking about this. Scattergrams. You've probably caught on that I'm a visual kind of thinker. I like to illustrate statistical concepts with graphs whenever possible. Before you compute Pearson correlation, you should always first verify that the relationship between the two variables is linear. To do this, you should create a scattergram. Scattergram is also called a scatter diagram, also called a scatter plot. It's always a good idea to create a scattergram before you actually compute a Pearson correlation. At a minimum, it'll show you whether you've got the kind of relationship between the variables that you really need to have if you're going to compute Pearson correlation coefficient. I'm on page 180-9 now. Top of 180-9. Definition for a scattergram is a type of graph in which each plotted point represents an individual observation. Each plotted point typically represents an individual person in the typical study in psychology. There's exceptions to this, but in most cases, a dot is going to represent a person. And each plotted point shows you where this person stands on the two variables being correlated. Example of a scattergram. Figure 180.1, minutes of weekly exercise as a function of health motivation. On the next page, we have our first scattergram. I am on page 180-10. Here's a scattergram. What does the caption say? Minutes of weekly exercise as a function of health motivation. I've scribbled in some words here to make a point about the way we typically write labels for figures in psychology. The criterion variable, name of the criterion variable typically appears first in front of the words as a function of. And then the name of the predictor variable typically appears second after the words as a function of. In our analysis, minutes weekly exercises, criterion variable, health motivation is predictor variable. In our graph, on the x-axis, the horizontal axis, we are plotting values of health motivation. It's standard to put the predictor variable on the x-axis. Health motivation scores 1, 2, 3, 4, up through 7. Higher scores represent greater degrees of health motivation. We're plotting on the vertical axis, the y-axis, our outcome variable, our criterion variable, minutes of weekly exercise. Higher values indicate more minutes of exercise. The way to make sense of a scattergram is to focus on just one dot. Let's, for example, focus on this one dot that's in the upper right corner. This dot represents a person. Location of the dot in two-dimensional space tells us where that person fell on both the predictor variable and the criterion variable simultaneously. This dot is directly above a score of like 6.0 on health motivation. So this dot represents a person who scores high on health motivation. By the same token, if you were to draw an imaginary line to the left, we would see that this dot represents a person who also scores high on minutes of weekly exercise. This person apparently gets somewhere in the ballpark of 300 minutes of exercise per week. By the way, it probably goes without saying that these data are totally fictitious. You gave a questionnaire like this to a sample of typical college students, you're not going to find a whole lot of people that exercise 300 minutes per week. But this will illustrate the concepts that I want to illustrate. So this one dot represents a person who scores high on health motivation, also scores high on minutes of weekly exercise. This dot represents a different person. This individual scores low on health motivation, also scores low on minutes of weekly exercise. Each of the remaining dots can be interpreted in the same way. Notice there's a trend illustrated here. A little bit later, we'll see, we call this trend a positive correlation. There's a trend that as health motivation goes up, minutes of weekly exercise goes up. People that score high on health motivation score high on minutes of exercise. People that score low on health motivation tend to score low on minutes of weekly exercise. We've got a trend here. A little bit later, we'll talk about how we make sense of these trends. I'm still on page 180-10, toward the bottom, page 180-10. To get a large Pearson R, scatterplot should look like a skinny slanting football. This is actually an important point. I want to dwell on this for a second because this issue is going to come up at a couple of times during my lecture. To get a large Pearson correlation coefficient, and if you're the researcher, you probably do want to get a large Pearson correlation coefficient. To get a large Pearson R, scatterplot should look like a skinny slanting football, and that is pretty much what we have here. Notice it is slanting, it is sloping. As scores on one variable go up, scores on the other variable go up. It would also be okay if it was slanting in the opposite direction, as long as it shows some kind of slant, some kind of slope. Other things held constant, we want it to be skinny. We're going to see that the skinnier that this sloping scatter plot is, typically the stronger the correlation coefficient is going to be, the tighter the relationship between the x variable and the y variable. So this issue will come up at various points in this lecture. To get a large Pearson R, scatter plot should look like a skinny slanting football. Let's go to page 180-11. 180-11 just puts into words what I just talked about a minute ago. In the figure, each data point represents individual participant in the study. Location of a data point illustrates where that subject falls on the y-axis, minutes weekly exercise, and the x-axis, health motivation simultaneously. Here we go. Here's some fill in the blanks. I'm halfway down page 180-11. You should always create a scattergram prior to computing correlation coefficient. Scattergram allows you to check a number of things. Scattergram allows you to verify that the relationship between the two variables is linear. In a minute, I'll give you a definition for linear, and I'll show you pictures that illustrate what it means like when you've got linear relationship. Creating scattergram allows you to verify your data do not display homoscedasticity. There's a word you don't use every day. In a minute, and I'll define that, and we'll see what it looks like. Finally, creating a scattergram allows you to identify possible outliers in the data set. Outliers are almost always bad news. They can severely bias your results. You need to know whether you have outliers before you start talking about your results with anybody else. In a minute, we'll see what outliers look like. Let's begin with that first term, linear relationship, and let's define that term. With a linear relationship, the y-scores change in only one direction as the x-scores change, making it possible to fit a straight, best-fitting line through the center of a scatter plot. That's our definition for linear relationship. I've actually got a couple of definitions here before we get to my sample graphs, and I think I'm hearing feedback from students saying that they wish it wouldn't jump around so much. So let's go ahead and rather than jumping to the figures that illustrates linear relationship, let's first define our remaining terms, and then we will go to the graphs that illustrate what linear relationship and so forth looks like. Here's the next term, next characteristic that you, in this case, don't want in your data set, homoscedasticity. Homoscedasticity is a bad thing. It means that the variance of the y-scores is different at different values of the x variable. I do not expect that to make any sense just yet. In a minute, I'll show you a graph that hopefully will allow it to make sense. And finally, here is the serious bad boy of statistics, outliers. Outliers are atypical, unusual data points. It causes the correlation coefficient to be biased or misleading. Outliers are almost always bad news. Outliers can be humiliating. If you publish some article, didn't realize the results you got were actually totally due to outliers, and later have to print a retraction. So we'll see what outliers look like. What's important about them is they can cause the correlation coefficient to be biased or misleading. Having defined our terms, let's look at some graphs that illustrate these terms, that illustrate what does it look like when you have linear relationship, what does it look like when you have homoscedasticity, and so forth. I'm on page, well, let's see, 180-12 says following figure illustrates these concepts. Then 180-12, as I recall, is a totally blank page. I should probably just pull that out of the course pack. Now we can illustrate these concepts. I am on page 180-13, and we've got a number of figures here. The top figure on page 180-13 illustrates linear relationship. This is a good thing. This is what you want. With a linear relationship, it's possible to fit a straight fitting best line through your scatter plot. Notice I've got this nice angled scatter plot. It is possible to fit a straight line right through the middle of it. That's kind of a rule of thumb way of knowing where you've got a linear relationship. Now, as long as we're looking at it, let's go back and look at my definition that I gave you before to make sure that that definition makes sense. This was on page 11. It said, and this is the definition I showed you before, with linear relationship, y-scores change in only one direction as the x-scores change. What does he mean by that? The y-scores change in only one direction as the x-scores change. Now, again, back page 180-13, the y-scores change in only one direction as the x-scores change. As the x-scores increase, as the x-scores go up, the y-scores change in only one direction. They only go up. As the x-scores go up, the y-scores only go up. Now, it would still be okay if it was going in the opposite direction. If we had a scatter plot with this kind of an angle, and as the x-scores went up, the y-scores only went down, that would be fine. That would still be a linear relationship, as long as it goes in only one direction. To understand what a linear relationship is, let's contrast it with bad situation. Nonlinear relationship, also called curvilinear relationship. Still on page 13, and bottom half of the page, we have this nonlinear relationship. Notice I've changed variables. This is all totally fictitious, but I think semi-reasonable. What if we looked at the relationship between current physical health and minutes of weekly exercise? Might we see a curvilinear relationship between those two variables? Maybe it goes like this. If somebody scores really low on current physical health, they don't get any exercise at all because they're in too bad shape to get any exercise at all. Maybe their conditioning is so poor they get winded immediately. But as current physical health goes up, as current physical health increases, minutes of weekly exercise increase. Now we're looking at people that are more fit, and yes, they can engage in more exercise, they engage in more exercise, engage more, until you reach some midpoint. Now remember, this is totally fictitious. I don't think you'd actually find this in the literature. But you reach a midpoint. Now, these are the people that are moderately physically healthy. They're engaging in a lot of exercise. And now, as current physical health further improves, minutes of weekly exercise actually goes down. How could this be? Well, maybe what's going on is these people figure, look, I'm in perfect health. I don't need to jog. I don't need to exercise. Maybe the people that think they're in perfect physical health don't exercise at all because they feel like they don't need it. If this phenomena were going on, you would see a nonlinear relationship. As the x-scores increase, as the x-scores change, the y-scores change their direction. As the x-scores go up, at first the y-scores go up, and then the y-scores start going down. That is a nonlinear relationship. As the x-scores increase, the y-scores change their direction of change. Nonlinear relationships. Very fascinating when you get nonlinear relationship. I label it bad here, not because you don't want to get them, but just if you've got nonlinear relationship, must not analyze the data using the Pearson correlation coefficient. You get very misleading results. There are other statistics you could use to investigate nonlinear relationship. Here's an example of an appropriate correlation coefficient to use if you've got a nonlinear relationship. The eta coefficient, sometimes called the correlation ratio. The eta correlation coefficient is appropriate for nonlinear relationships like this. If you find yourself in the happy situation where you have one, don't use Pearson R, instead use eta or some other statistic that's appropriate for nonlinear relationship. We're still talking about conditions you do want and don't want if you're going to compute Pearson R. I'm on page 180-14. We're now going to look at homoscedasticity. Definition for homoscedasticity. The variance of the y-scores is the same at each value of the x-scores. Homoscedasticity, the variance of the y-scores is the same at each value of the x-scores. Think about it this way. We're looking at health motivation, relationship between it and minutes of weekly exercise. Focus only on the people that score low on health motivation. People had a score of 2.0 on health motivation. Notice what the variance of their scores is on minutes of weekly exercise, our y variable, our criterion variable. Just to keep it rough rule of thumb, notice the difference between the lowest y value here and the highest y value here. On my computer screen, it's a difference of about 1 inch. So let's think of the variance of scores. Variance of scores on minutes weekly exercise. When we look at the people with low health motivation, variance is represented by about 1 vertical inch. Now, look at the people that have medium level of health motivation, a 4.0 in health motivation. What's the variance of their scores on y? Well, how spread out are these scores on y if I look at only the people that have moderate level health motivation? Once again, the spread of the scores amounts to about 1 vertical inch on my computer screen. And then finally, what about people that have a high level health motivation, above a score of 6? What's the variance of their scores on y? It's the spread of scores between this score and this score. It's about 1 vertical inch on my computer screen. In other words, the variance of the y-scores is pretty much the same no matter what their health motivation score is. Low health motivation has a certain variance. Medium health motivation has about the same variance on minutes of weekly exercise. High health motivation has about the same variance on minutes of weekly exercise. This is homoscedasticity. The prefix homo means the same. Homoscedasticity means variance of y is pretty much the same no matter which value of x you're looking at. Homoscedasticity is good. That's a characteristic you want your data to have if you're going to compute Pearson correlation coefficient. What you don't want is on the bottom half of page 14. And that is heteroscedasticity. Defined that earlier, let's define it again. Heteroscedasticity means variance of the y-scores is different at each value of the x-scores. This is bad. If you've got heteroscedasticity, you don't want to compute Pearson correlation. We have a different predictor variable here. Different predictor variable, current healthy diet behavior. This variable basically reflects how good is your diet. If you score low on current healthy diet behavior, you eat lousy food, junk food all the time. Score high on current healthy diet behavior, you eat good food all the time. We're looking at the relationship between current healthy diet behavior and minutes of weekly exercise. We have heteroscedasticity. First of all, focus only on the people that score low on current healthy diet behavior. What's the variance of their scores on y, minutes of weekly exercise? Well, there's hardly any variance of their scores on y. It amounts to about 1/2 of an inch on my computer screen. Very little variance on minutes of weekly exercise when we look at the people that score low on current healthy diet behavior. But what about people that score high on current healthy diet behavior? People that have a score of like 6 on current healthy diet behavior. What's the variance of their scores on y? What's the variance of their scores on minutes of weekly exercise? It is tremendous variance. Look at the range between the lowest score and the highest score. It's like 2.5 inches on my computer screen. So when I look at people that score high on healthy diet behavior, great deal of variance on minutes of exercise. Look at people that score low on current healthy diet behavior, very little variance on minutes of weekly exercise. I have heteroscedasticity. The prefix hetero means different. My variance is different depending on whether I'm looking at people that score low on X versus people that score high on X. This is bad. If you've got heteroscedasticity, you can't compute Pearson R. The truth is there is no easy fix for this. Statisticians and researchers will typically do some kind of transformation of the data in order to be able to analyze their data, and lucky for you folks, that goes beyond what we're going to cover in our PSYC 299 class. So we've talked about homoscedasticity, heteroscedasticity. Now we come to the concept of outliers. Now this issue of outliers come up earlier in the semester, but it's especially worrisome if you're thinking about computing Pearson correlation coefficient. You compute Pearson correlation coefficient, you've got to look at your data first in a scatter plot and make sure you don't have outliers, because if you do have outliers, you might get misleading statistic. What do we have here in the upper part of 180-15? It says an outlier here, and I'm pointing at this data point, this person, an outlier here would cause the sample correlation coefficient to be misleadingly small. What do I mean by that? Now, first of all, look at most of the data points. Most of the data points are in this body of the scatter plot. It's a sloping, skinny scatter plot. This is good news. This kind of scatter plot would typically give you a really big, strong correlation coefficient of 0.8, maybe 0.9. That would be good news for you. However, unbeknownst to you, because you did not do the scattergram ahead of time, you didn't know it, you've got an outlier here. This outlier tricks the statistical algorithm into thinking that you don't have a skinny sloping football. You have kind of a roundish sort of a football, and the statistical application is going to compute a smaller Pearson correlation coefficient than it really should have reported. You should be getting a Pearson correlation of like 0.80, but when the statistical application takes this outlier into account, it gives you a smaller correlation coefficient. Instead of 0.80, maybe it gives you 0.50, and that's misleading. If you looked into this outlier, 8 times out of 10, you find out it's because you keyed the wrong number. It's not because there really is somebody in this location. You just either keyed your X variable wrong or your Y variable wrong. You need to create a scatter plot first, make sure you don't have an outlier there. This is actually not even the worst case scenario. This is the worst case scenario. I'm still on page 15. Bottom half of page 15. What does it say? An outlier here, and this arrow is supposed to be pointing at a data point right here. Outlier here would cause sample correlation to be misleadingly large. Now imagine this. Imagine in reality there is no correlation between health motivation and minutes of weekly exercise. If you have a scatter plot that is round like this, the statistical application would normally say your correlation coefficient is 0, indicating there's no relationship between health motivation, minutes of weekly exercises at all. That's what you should be reporting, 0 correlation. But unfortunately for you, you didn't do a scatter plot ahead of time. You didn't realize that you had miskeyed results for one of your subjects, and it created an outlier up here. Now, you've created some fictitious person that supposedly scores really high on health motivation, really high on minutes of weekly exercise. This outlier tricks your statistical application into thinking you've got a stronger correlation than you really do. Statistical application might say the correlation between your two variables is 0.30. That might be big enough to be statistically significant. You're all tickled, you publish it. A couple of years later, some graduate student somewhere reanalyzes your data and sees, oh, you had an outlier here that you didn't know about. You reanalyze the data without the outlier, you find your correlation is actually 0. You have to print a retraction that these results that you presented a couple of years ago were totally false because you were too careless to take time to create a scatter plot. So you need to do scatter plots for all kinds of reasons. Among the most important reasons, make sure you don't have outliers. So what do you do if you have outliers? The answer is it depends. 8 times out of 10, it's because you miskeyed the data. If that was the case, then key the data correctly, or if it's somebody you don't have the data for at all, drop that individual. When you go into graduate school, you'll learn that there are more sophisticated ways of dealing with outliers and missing data. Mercifully for Psych 299, you folks don't need to worry about those more sophisticated processes at this point in your education. So that was page 15, illustrations of outliers, heteroscedasticity, nonlinear relationships, and such. Let's continue. I'm now on page 180-16 at the top. This is a biggie. You can assume there's going to be questions on the test in which I describe fictitious study. I give you a correlation coefficient. It'll be your job to tell me, to just look at the correlation coefficient and tell me about the nature of the relationship between the two variables. Is it a positive correlation, negative correlation? Somebody scores high on X, they probably score high on Y, or do they probably score low on Y? Those kinds of questions. That all comes under the general heading of interpreting the sign and the size of the correlation coefficient. I'm on page 180-16. What do we have? Pearson correlation coefficient ranges in size from negative 1.0 through 0 through positive 1.0. Sign and size of the coefficient tells you about the nature of the relationship between two variables. Pearson correlation coefficient is a neat statistic. It is usually presented as a 2 decimal place statistic, such as the correlation between the variables was positive 0.21, or the correlation was negative 0.77. Just looking at those two digits, a seasoned reader of research can tell you about the trend that you have, whether it's a positive slope or a negative slope. They can tell you how strongly the two variables are correlated, whether it's a weak association or a tight association. I want you folks to be able to do that. It involves interpreting sign and size of the correlation coefficient. I'm still on page 16. First up is the sign of the correlation, what some textbooks call the direction of the correlation. Sign of correlation coefficient is always either positive or negative. What does it mean if you have a positive correlation? With a positive correlation, high numbers on one variable are associated with high numbers on the other variable. When you look at the scatter plot, you can see that as values on one variable increase, values on the second variable also tend to increase. You've already seen examples of positive correlation. Figure 180.1 presented earlier showed one. I reproduce it here on page 180-16-B. I think I've told you in class, anytime you've got page numbers where I've added letters at the end, that means that I had the right idea that I really should reinsert a figure at this point, so I have to add letters to them so that I can keep things in sequence. You saw this figure previously. It illustrates positive correlation. Correlation between health motivation and minutes of weekly exercise. We know it's positive correlation because as scores on health motivation goes up, there's a trend that scores on minutes of weekly exercise also go up. Now, I'm not saying it's cause and effect. I'm not saying that health motivation causes minutes of exercise to go up. I'm just saying graphically, when you look at it, you can see people with high scores on health motivation have high scores on exercise. Those with low scores on health motivation have low scores on minutes of exercise. That is what we mean by positive correlation. I don't believe I've shown you an example of a negative correlation before, so let's see our first negative correlation. Negative correlation, sometimes called an inverse correlation. There's a fill in the blank for you. Negative correlation, also known as inverse correlation. And let's find out repeater definition, page 17. With a negative correlation, high numbers on one variable associated with low numbers on the other variable. As values on one variable increase, values on the second variable tend to decrease. Here's an example of two variables that might have a negative correlation. Correlation between minutes of weekly exercise and hours spent working at a desk job per week. It makes sense. Those individuals that spend many hours working a desk job probably have little time for aerobic exercise, so the relationship should be negative. The more hours per week you have to spend working a desk job, probably the fewer minutes of exercise you're going to get. That's reasonable. Following figures a scattergram that illustrates negative correlation between these two variables. Page 18. Here is my negative correlation. Minutes of weekly exercise as a function of hours spent working at a desk job, negative correlation. Same outcome variables before. Minutes of weekly exercise that you get, higher values mean you get more exercise, but a different x variable. X variable is now hours spent working at a desk job per week. These are the people that don't work at a desk job at all. These are the people that spend 20 hours a week working at a desk job. These are the workaholics that spend 60 hours a week working at a desk job. Notice as hours spent working at a desk job increases, minutes of weekly exercise like jogging decreases. Makes sense. If you're working 60 hours a week at a desk job, you don't have time to do any jogging, so your scores are down in this lower size. Negative correlation can be just as strong as the positive correlation. All it means is the trend goes in a different direction. That's a negative correlation. Now, so far we've talked about sign of the correlation. Sign of the correlation simply tells us what's the direction of the trend. Maybe more important is this concept. On page 19, second characteristic of a correlation coefficient I want you to be able to interpret. I want you to be able to interpret size of a correlation coefficient. Size refers to how large a correlation is in absolute value. To refresh your memory, what absolute value is? Absolute value means ignore the positive or negative sign. Just focus on how big is the number, disregarding whether it's positive value or negative value. How big is the number? Size refers to how large is the correlation. And fortunately for us, the interpretation of the size of correlation is fairly intuitive. A correlation of 0 means there's no relationship between the two variables. You've heard somebody say there's 0 correlation between this variable and that variable. They are saying that, yeah, literally the correlation coefficient is 0, no trend at all. In general, the larger the size of the correlation coefficient in absolute magnitude, the stronger the relationship between the two variables. Correlation of 0.10 is pretty small correlation. That's kind of close to 0, isn't it? Correlation of 0.10 is generally considered to be a relatively weak relationship. A correlation of 0.50, notice I've scratched out the 0.70 that was there before and put in a more realistic 0.50. Correlation of 0.50 is generally considered to represent a very strong relationship. I'm going to show you some scattergrams that illustrate different strengths of relationship. Let's go to page 180-20. Now, these scattergrams are fictitious, and the correlation coefficients that I attach to them are also fictitious. There won't be any questions on the test where I show you a scattergram like this and you have to tell me exactly what is the correlation coefficient, because nobody can do that. Nobody can look at a scattergram and know exactly what the correlation is. But I do expect you to know the difference between a scattergram that shows a weaker relationship, maybe a 0 relationship, versus a scattergram that shows a stronger relationship. On page 180-20, top of the page, figure 180.4.A. The correlation is 0, no relationship, no effect. Imagine in some parallel universe, you did this investigation and you got a round scattergram like this. Round scattergram is bad news. It means there's no trend. It's not the case that people that score high on health motivation are more likely to exercise more. It's not the case that those that score low on health motivation are likely to exercise more. 0 relationship. If you know somebody score on health motivation, it does not allow you to predict how much exercise they get at all. Correlation is 0. Still on page 20, bottom half. Now we're getting a little something. We've got a little bit of shape to this scattergram. The correlation is now 0.10. This is what Jacob Cohen calls a small effect size. A little bit later I'll talk about Jacob Cohen and his criteria for interpreting correlation coefficients. There is a little bit of a trend. What did I write here? Scattergrams for correlations of various sizes. There's a little bit of a trend here. Somebody who scores high on health motivation is somewhat more likely to engage in exercise. Those that score low on health motivation are somewhat less likely to exercise, but it is not what you could call a tight relationship. Let's go to page 180-21. Now it's getting tighter relationship. Correlation 0.30 is what Jacob Cohen calls a moderate effect size. Notice now our football is getting a little bit skinnier. Now, if we know somebody scores high on health motivation, we can predict where they probably score on minutes of exercise with a little bit more precision. Bottom half of the same page, correlation is 0.50. This is what Jacob Cohen calls a large effect size. Notice our football is still sloping and it is getting skinnier. That means we can predict with more accuracy. If somebody scores high on health motivation, we can predict that they'll score high on minutes of exercise, and our predictions are getting more accurate. More accurate still, I'm on page 180-22. Correlation is 0.90. I can't think of a time I ever did a study and I got correlation of 0.90 between two variables. Real variables are almost never correlated that strongly in real world research. But if you had a correlation of 0.90, scattergram probably looks something like this. Notice it's still slanting, but now it's a very skinny football. If somebody scores high on health motivation, we can predict where they probably score on minutes of exercise with great precision. That's strong correlation. What's the upper end of correlation coefficient? Upper end of correlation coefficient is plus or minus 1.0. Plus or minus 1.0 is a perfect association. In this case, it's plus 1.0. Notice every single dot falls on a perfectly straight line. If I know where you stand on health motivation, I can predict where you stand on minutes of exercise with perfect accuracy. If you have a score of 6.0 on health motivation, I draw a straight line up to where it intersects with this line. I draw a line over to the left, and wherever it intersects with minutes of exercise, that's my prediction of how many minutes of exercise you get. So if you had a score of 6.0 on health motivation, I predict you get 250 minutes of exercise, and that prediction would be perfectly accurate. There'd be no error to it at all. That is what you get when you have perfect correlation coefficient of 1.0. Now, a minute ago, I alluded to Jacob Cohen and his criteria for interpreting correlation coefficients. You've heard the name Jacob Cohen earlier in this semester. He's a very influential writer. He's now deceased, but wrote books and articles that still influence us today. He talked about the importance of assessing effect size. He said anytime you do an investigation, you want to assess how strong or weak is the effect size, you should always compare your results to the results that were obtained by other researchers that investigated similar variables, and compare your results to the effect sizes that they got in previous studies. If you're in some new field where nobody's done research in your area before, I give you some last resort criteria that you can use to interpret your statistics. For better or for worse, a lot of researchers use his last resort criteria. A lot of researchers use it as their first resort in interpreting results. Something most statisticians say is a bad idea. Good idea, bad idea. I want you to know what his criteria are, and this is how he defined it. Coeff provides following guidelines for interpreting size of the effect reflected in correlation coefficient. If the correlation is plus or minus 0.10, that's the benchmark that Jacob Cohen gives us to label a small effect size. So if it's bigger than 0.10 but not as big as 0.3, we'll call that small effect size. If it is bigger than plus or minus 0.3 but not as big as 0.5, if it's bigger than plus or minus 0.3, we'll call that moderate effect size. And if it's bigger than plus or minus 0.5, we'll call that large effect size. Now, you've heard me say this before, and I'll say it again. The word effect, take that word with a grain of salt in this case, because correlational research typically provides only weak evidence of cause and effect relationships. The term effect size is used in all kinds of research, including non-experimental research. It's okay to call it index of effect size. But remember, if all you did was a simple correlational study, you probably don't have much evidence of cause and effect. I've talked about prediction, and that naturally segues to the topic coefficient of determination. If you have a correlation coefficient, Pearson correlation coefficient, you should be able to turn that into a coefficient of determination. You could assume there'll be questions dealing with that on our upcoming test. Definition. Coefficient of determination is the percent of variance in the criterion variable that's accounted for by the predictor variable in a correlational analysis. Coefficient of determination is computed by squaring the correlation coefficient R. This is going to be one of the simpler statistical mathematical analyses that we will do in this course. If you've got a Pearson correlation coefficient, it is easy to turn it into coefficient of determination. On page 24, we have the formula. Coefficient of determination is computed by taking the Pearson correlation coefficient R and squaring it. Once you've done that squaring, you've got the coefficient of determination. This means if the correlation between the two variables is 0.50, coefficient of determination is 0.25. How do I know that? Take 0.50, punch it into your calculator, square it. If you know how to do it with a scientific calculator, do so. If you're not so familiar with scientific calculator, you can square it just by multiplying. 0.50 times 0.50 gives you 0.25. My coefficient of determination is 0.25. Correlation is 0.50. You can easily turn that into coefficient of determination 0.25 and do that with any correlation coefficient. I want you to be able to interpret coefficient of determination, understand what it means. I'm still on page 24. Coefficient of determination communicates the percent improvement in predictive accuracy. Coefficient of communication communicates the percent improvement in predictive accuracy. Now that statement by itself doesn't mean anything, but I'm going to give you some examples. Compare the following two situations. Situation 1 is going to be a situation in which you have 0 predictive accuracy. Situation 1. Imagine that the correlation between variable x and variable y is equal to 0. I want you to take that and turn it into a coefficient of determination. Well, it's easy. You just square it. If the correlation is 0, 0 squared is still 0. So my coefficient of determination is 0. What does that mean? Let's put it in verbal terms. In this situation, my coefficient of determination is 0. X does not account for any of the variance in y. Knowing where a participant stands on x does not allow you to predict where they stand on y with any accuracy at all. Do I have a scatter plot that illustrates that? I do. Very good. Let's make sure you've got this definition. Going back to wherever I was, 24, bottom page 24. Let's make sure you have a minute to fill in that blank. Bottom page 24. If the correlation between x and y was 0, that means coefficient of determination is also 0. X doesn't account for any of the variance in y. Knowing where somebody stands on x does not allow you to predict where they stand on y with any accuracy at all. I illustrate this on page 180-24b. Here's a situation where there is no relationship between the two variables. Situation 1, no relationship between the variables. Imagine in some universe, the correlation between health motivation and minutes of exercise was 0. Let's look at the scattergram here. Oh, it's a round scattergram. That's bad news. There's no trend at all. Knowing somebody scores high on health motivation does not allow me to predict where they stand on minutes of exercise with any kind of accuracy. Knowing where they stand on low health motivation does not allow me to predict where they stand on minutes of exercise with any accuracy. Round scattergram means correlation between the two variables is 0, means coefficient of determination is 0. Health motivation does not account for any of the variance in minutes of weekly exercise. Now, that's my bad prediction situation. We're going to contrast that with a better prediction situation. I'm on page 180-24c, situation 2. Situation 2, the correlation between variable x and variable y is equal to 0.50. So the coefficient of determination is computed in this fashion. The correlation was 0.50. The way you turn correlation into a coefficient of determination is by squaring it. 0.5 times 0.5 is equal to 0.25. Okay, my coefficient of determination is equal to 0.25. Well, so what? What does that mean? On page 180-25, I talk about what that means. In the second situation, coefficient of determination is 0.25, which means x now accounts for 25% of the variance in y. Knowing where somebody stands on X does allow me to predict where they stand on Y with some accuracy. Specifically, it allows me to predict where they stand on Y with 25% more accuracy than in situation 1, situation where I had zero correlation. What do you mean by predict? You keep using that term. Let's put this in black and white. I'm still on page 25. What do you mean by predict? As an illustration, if the correlation between X and Y is positive correlation, like positive 0.50, then you'd predict somebody probably had relatively high score on Y if they had relatively high score on X. You'd predict they probably had relatively low score on Y if they had relatively low score on X. I illustrate that with an X transparency. No, it's not a transparency. This just reflects back to the fact that these notes are so old that they actually began as transparencies back when we used transparencies projectors. Before we look at it, what else do I say? You'll learn more about how exactly one makes predictions when you study bivariate regression, which is going to be one of your next modules. The upshot is this. Before we get to the upshot, let's look at this scattergram where we can actually do some predicting. You've seen the scattergram a million times before in this lecture. I show it again just to illustrate what I mean by predicting. This is the scattergram where we're looking at the relationship between health motivation, minutes of weekly exercise. Health motivation is the X variable, minutes of exercise is the Y variable. If somebody scores high on X, we predict they probably score high on Y. The way you do it is you take their score on X. Here's a person that got a score of 6.0 on X. If they have a score of 6.0 on X, what's our prediction of where they stand on Y? We draw a straight line over. We see where it intersects with the Y-axis, intersects at about 250. So if somebody had a score of 6.0 on health motivation, I would predict they probably have a score of about 250 minutes on the Y variable, minutes of weekly exercise. If somebody had a low score on X, somebody had a score of 2.0 on health motivation, draw a straight line up, draw a straight line over to the left. If somebody scores 2.0 on health motivation, I predict they only score about 80 minutes on minutes of weekly exercise. That's what we mean by prediction. Notice in this situation, I can make semi-accurate predictions because I've got a trend here. I have a relatively skinny slanting football. If I've got a sloping football, slanting football, the skinnier the football is, the more accurate my predictions are going to be. In this situation, I'm making more accurate predictions than I made back in the situation where I had a round scatter plot, where the correlation was 0. In this situation, the correlation is 0.50. Coefficient of determination is 0.25. So in this situation, my predictions are 25% more accurate than they were in the situation where the correlation was 0. But wait a minute, how do you know 25%? Because that was the coefficient of determination that I computed. Let's back up and make sure that that's what my notes said. I'm going back to page 180.25. In situation 2, where I actually had a correlation between the two variables, X now accounts for 25% of the variance in Y. Knowing where somebody stands on X does allow me to predict where they stand on Y with some accuracy. Specifically, it allows me to predict where they stand on Y with 25% more accuracy than in situation 1, the 0 correlation situation. How do you know 25%? Because that is what my coefficient of determination was. That is the coefficient of determination. That is how you make sense of it. That is how we relate coefficient of determination to the nature of a scatterplot, what a scatterplot looks like. Now, I have more lecturing to do in this module. We're still in part 180. I'm a little more than halfway through it. That's long enough for one setting, so I'm going to end this video. We'll call it video part 1, and there will be a part 2 to the video where I go through the second half of module part 180.